on categorical Hooft expansion. So please.
Okay, so I would like to talk about chiral gauge theory now. So these are two-dimensional quantum field theories which are holomorphic. Mathematically, you can think about vertex algebras, vertex operator algebras, chiral algebras, or factorization, holomorphic factorization algebras on the complex plane. And I want them to be gauge theories. This is sort of the chiral analog of a quantum Hamiltonian reduction. So you have a free chiral algebra, a chiral algebra which is a bunch of beta gamma systems, if you want, and you want to do a quantum Hamiltonian reduction to describe essentially a beta gamma system whose target is a symplectic quotient. So roughly the data is a gauge group and a symplectic representation, but there is an anomaly cancellation condition which appears in this chiral situation. It's usually an anomaly that people are familiar with in the context of curved beta gamma systems. And this anomaly requires the representation to be somehow constrained. But a simple way to get around that is to consider super representations. So to put fermionic matter fields too. Anyway, so we have some matter fields, these XAs, which have the usual OPE of a beta gamma system of symplectic bosons. And there are some ghosts to impose the quantum Hamiltonian reduction. Roughly, B would be a restricted transformation which sends B to the moment map and uses C to impose gauge invariance. So this, let me say it again. So the nice feature of these theories is that they're essentially free theories plus a differential. So calculations are very straightforward. The operators in these chiral algebras are, again, traces, single traces, and they're polynomials.
David, I missed where is the group or Lie algebra? This XA of Z, the occurrence with coefficients in the Lie algebra, or what?
I'm doing, as usual, a UN gauge theory or something like that. And then everything is matrices. So everything is a joint field.
So then again, XA of Z, it's a series like in Z or whatever, negative power of Z.
If you want to think about
coefficients which are matrices, yeah?
Yes, yes.
Okay.
That's right.
In general, elements of the Lie algebra.
Absolutely.
Okay.
And so are B and C, except they're fermionic. Okay. And you build polynomials for these X's and B's and C's, organized as traces. And you can take products of traces too. And this gives you also to the operators in the chiral algebra. The traces are sort of the strong generators of the chiral algebra. And so you get these traces modulo a differential, which I will describe momentarily. And if you prefer to think about vertex operator algebras, then you say, okay, I have modes, which are the modes of these operators, contour integrals of Z to the n times your trace as a function of Z. Any questions?
So H here is a complex number. It doesn't have to be small.
It's a formal parameter. I'm always working in perturbation theory, so everything is defined over formal power series in each bar. So it's a vertex alpha over C of each bar.
Okay.
Well, can I ask a quick question? How does this setting relate with the gauge theory?
So I have essentially gauge fixed the gauge theory. The gauge field is gone, and the only thing that's left is the ghosts.
So you have a base manifold, or you have a base super manifold, or
right. You can think about it as a beta gamma system valued in a symplectic reduction. So you take some flat, some symplectic vector space, and you do a symplectic quotient, and then you do beta gamma system valued in that.
But these variables are still running on the Riemann surface in general. Z.
Yeah, that's right. So you get the holomorphic factorization algebra. You can study OPs or you could put it on the Riemann surface and study conformal blocks. Absolutely.
Yeah, thank you.
Today I will only do the complex plane or the Riemann surface or the CP1, the sphere. Okay. So in the same way as in the matrix model, the whole matrix model could be presented in terms of a 3D Calabi-Yau algebra. In the case of these 2D theories, the whole data can be organized into a 2D Calabi-Yau algebra. There is some extra constraint, as I said, because you want anomaly cancellation. I will not try to describe what that means. Essentially, the number of arrows should be, the graded dimension of the spaces of arrows should be just right.
And this algebra A, it's what?
You can think about it as a graded ADE algebra.
No, how it comes from the vertex separator algebra data.
The x's are the arrows and the gauge fields are the nodes. So
yeah, it's 2D no potential. It's just
that's right.
Just a symmetric quiver, if you'd like.
Yes, yes. So, and the simplest examples are precisely, a node with two arrows, or if you want C of theta 1, theta 2. Which is associated to the 2D Calabi-Yau C2. Other canonical examples are C2 mod gamma, ID and the AD singularities.
And how do you see it in terms of the... you take just invariance?
Yeah, you have a whole bunch of gauge groups, and you have fields between pairs of the nodes.
Bunch means that they correspond to the whatever Dynkin diagram of gamma.
Yes, absolutely.
Yeah.
And there is a variant where you allow yourself fermionic arrows, and so you could do something like, I don't know, 4 bosonic arrows and 2 fermionic ones. This would give you non-commutative beasts, which seems somewhat interesting, but for which I don't have a geometric interpretation.
Mm-hmm.
Okay, so the operators were traces. So again, the operators are pretty much labeled by cyclic cohomology. Let's say cyclic complex, the cyclic complex of A of Z instead of A. So polynomials in Z valued in A. So we have an OP and we have a differential. And if you try to compute them, it's messy. There are a lot of with contractions to do. It's a sum of Farman diagrams. You can take the leading order at large N, and you get what's called a Poisson-Chiral algebra. So
sorry, where is N here?
N is in the gauge group. So the gauge group is UN.
You mean that it affects only differential?
Yes. Well, it affects. So you do it to compute the OPEs. You do it
N by N matrices. Yeah, all right.
So when you do the OP of 2 operators, there will be a term that might look like this. I contract 3 fields. I don't know. If the 3 fields were consecutive along the trace, I'm going to get factors of N. So overall, I get a factor of H bar because of how normalized the trace is. I get a factor of H bar for the propagators.
Yeah, probably it can be spelled like this. You have an algebra A. Let's forget about the grading. You take A tensor A, and the trace, instead of something which is trace of the AB, you take n trace of AB, something like that. You multiply, rescale probably the trace.
I prefer to rescale by factor of h bar. Like
But
here.
then this n and h bar should somehow talk to each other.
Well, and then the 't Hooft expansion says take, whenever there is a factor of n, combine it to the factor of h bar. So
Okay.
in this calculation, I have h bar squared from the definition of the operators, h bar cubed from the propagators, I have n squared, and then something is left, trace of some w, and I can rewrite it as nh bar squared then h trace, and in front of it there is just an h bar squared. So all the interesting part of the OPE has a factor of h bar squared in front.
In some power.
Right. That's right, but the leading one is always h bar squared. So if you take the OP of two operators, this will go like h bar squared times something plus higher order in h bar squared plus regular. The regular part is just literally the sort of the normal order product of O and O. So when you have a vertex algebra of this sort, there is this, you can get a Poisson chiral algebra. This is like a semi-classical limit of a vertex algebra, and it sort of focuses on this piece to define the lambda path.
Yeah, and lambda is n product with h bar in your.
No, lambda is just lambda bracket, so it's just notation. People define the lambda
it's
bracket.
not related to n and h bar. Okay.
No.
Let's
so there's
see.
a lambda bracket defined as the contour integral of lambda z.
They do not understand the notation, which would kill me. You have O of beta, which are local operators. That's okay. Yeah. What is O of alpha product lambda?
That's called the lambda bracket. It's a terminology introduced, I think, by Katz. And it captures the singular part of OPEs by doing this.
Okay.
So it's power series.
That's in Katz's definition of a conformal algebra, which he introduced.
Yes. Conformal algebra is another name. Yes. Lie conformal algebra. Or conformal algebra, sorry. Yeah, so there is an actual derivative and there is a lambda bracket which satisfies certain axioms.
Okay.
The messy associativity.
So which means that in the differential, because you add this different dg struct, nh bar has nothing to do with lambda.
Yeah. No, absolutely.
Okay.
That's right. So I have this differential of the Poisson chiral algebra, which takes an operator. There is a piece that is just, sorry, here I'm very sketchy. There is a piece which is linear in operators, which is the usual differential on the cyclic homology complex. There is a deformation controlled by an h bar, and there is a quadratic term that is also quantum correction.
Yeah, which probably, I don't know. Q, is it just O plus NH bar O or?
No, so here it was very schematic. This means I really meant, some differential.
Yeah, that's what I mean.
Yeah.
That should be some differential acting on the fields.
That's right.
Itself. So then it's a sort of,
This is just the
So then the closed, those which belong to cohomology with respect to Q should satisfy some sort of Maurer-Cartan equation.
Right.
Well, deformed because you have an
Yeah, it's deformed. That's right. So if you ignore the quadratic term and the NH bar term, this is the usual complex. So this is deforms the polynomials. Sorry, polynomials in HC. schematically.
Okay. All right. So what it has to do with the previous discussion?
Well, I've done the job. Right? I take my quantum field theory, I do the Hooft expansion, and I extract some structure in the leading order of Hooft expansion, which is a Poisson-Chiral algebra. This is,
all right.
yeah. So this is analogous to the Poisson phase space of pi's and tau's, which we were discussing before. We just need to find the correct way to say that. See, in the case of matrix models, the matrix model was a zero-dimensional thing, and holography produces a one-dimensional thing. So the quantum mechanics with a VLST operator, or classically a phase space with an Hamiltonian, a ordinal Hamiltonian, a derived classical mechanics. So here I start with 2 dimensions, one complex dimension if you want, and I need to add a real direction. So there is this idea that Kuyu, Zheng, and Hassan Khan had some recently. You can look at what's called a chiral Poisson sigma model. This is a 3-dimensional theory. It's defined on sort of complex plane times real line. And it's the analog of this classical mechanics system. It's a classical 3-dimensional theory. And the data of this theory is literally a Poisson-Chiral algebra. So you take a kinetic term and you add interactions. These interactions contain the Poisson bracket, the second term, and contain the differential, the last term. So I can, if I'm patient enough to compute this data, I can just convert it for free to a 3-dimensional classical theory. This classical theory sort of builds so that the Poisson algebra appears at the boundary. Ideally, if you could quantize this 3-dimensional theory, you might hope to find the full Hooft expansion of the chiral gauge theory.
But what kind of Hooft expansion you have for the chiral gauge theory in 2 dimensions?
Well, when you do the OPEs of products of these O's,
yeah,
you get it's a vertex algebra. So we had a vertex algebra over. So let me say it like that. So I have view A, which has a label n, and which is defined over C of H bar. So it's a perturbative view A.
Yeah.
In practice, everything is polynomial, but I'm gonna ignore that and take it as a formal power series.
All right.
And then the Hooft expansion reorganizes it as a view A, which now has a continuous parameter nh bar over C of H bar squared.
Yeah, but when you say Hooft expansion, you expand what?
The OPs, or the correlation functions. You can also do correlation functions or conformal blocks.
All right. So, yeah, okay. Is it, I'm confused, is it a sum over graphs or what?
Yeah, if you do correlation functions, it's sum of Feynman diagrams. If you do OPEs, it's also a sum of Feynman diagrams. The difference is that the sum over graphs, the correlation functions are Feynman diagrams without external legs, and the OPEs are Feynman diagrams with external legs. So your typical OP calculation will involve, a collection of traces.
I'm a bit confused that your Calabi-Yau is now 2-dimensional, yeah, because it's 2D Calabi-Yau.
Yeah.
And it looks as a C square.
Yes.
And in 3 dimensions, it was kind of very important to throw away the origin.
And now we're gonna take C3 minus C. So C2 minus the origin times C.
Okay. Okay.
That's right. Yeah, so you're gonna do something like that when you're trying to do. Sorry, mistake. When you try to do the P, you're gonna have a collection of traces on the left, a collection of traces on the right, and you're gonna sort of start doing with contractions to get another collection of traces. Okay, so that's right. So that's the next slide. How can I find this sort of structure from string theory or from something, geometry? I could study C3 minus C. I can take again the usual PCOV theory on C3 minus C and classical reduce on S3. So now I have a radial, I have a kinetic term that combines the del bar operator on C and the radial de Rham operator.
Sorry, David, you see, I have very bad geometric imagination. How you can reduce from C3 minus C to three-dimensional sphere?
No, so I want to reduce on S3. So
on S3, which means that you take S3, how it is positioned with respect to C3.
So take C2 minus the origin.
Okay. All right. So then you
C.
indeed, all right. So, okay. Okay. Get it. So then your C3 sits in the base of the product. Yeah.
Yes.
Okay, good.
And when you reduce, so now the del bar operator on C goes along for the ride. The del bar operator on C2 minus the origin breaks down into the radial one and into the Cauchy, tangential Cauchy-Riemann complex of S3. So this piece here, so now you have a three-dimensional
and beta, sorry about the question, the beta belongs to what?
Polyvector, say forms.
Forms on, in general, on C cube minus C, yeah?
Yes.
Okay.
So because you remove C, now you have forms.
Yeah,
like kernel on C2.
I hate to ask you, but D minus 1 is defined ambiguously. What is D minus 1 of D bar beta in the first integral?
Well, so
and then the last one as well. Actually,
beta are del closed forms.
But you
and
can
so
lift
del
it
inverse is almost defined. I know this is okay. I'm not responsible for defining BCOV theory.
All right, so read Costello and Lee. Okay.
But this is a pretty nice pairing on S3. In practice, if you look at it, you'll see that it's almost symplectic. Again, it misses a single form, or if you have a polyvector field, omega del time Martinelli del Z.
All right.
And this, as usual, when we match this symplectic pairing and stuff to the fields of the sigma model, I'm going to put together pi, tau, and an h bar. And an h bar is going to control this deformation. And nicely, in the case of matrix model, remember the corresponding deformation was definitely not geometric, right? It was the
some current, why not geometric? It was some sort of a delta form sitting on the origin, no?
Yeah, it's something whose del bar is the delta function of the origin. It's called omega the delta Martinelli kernel. It's a 0-2 form in C3 minus the origin. And so when you map it to a vector field, it's a polyvector field. It's a polyvector field of type 0,2. It's not a nice deformation of the system. On the other hand, here it's a polyvector field of type 1,1, which is a Beltrami differential. So in this particular situation, you can go from C3 mod C to SL2C. This is the effect of the deformation.
I go from what? I don't understand this.
So you take C3 minus C, you turn on this Beltrami differential, and you just look what you get.
And what? It's an SL2C matrix?
No, it's the manifold SL2C, is the Calabi-Yau manifold.
No.
The deformed conifold is the more difficult name, probably.
No, I do.
So there is a SL2C is a 3D Calabi-Yau manifold.
Yeah, this I understand, but I do not understand how this SL2C is related to what you said before about this slide.
So I'm just saying that after you identify what NH bar is,
Yes.
NH bar is the coefficient of a certain polyvector field.
Yes. Okay.
Which is this Beltrami differential. So turning on an H bar, setting an H bar to be a finite quantity instead of a formal variable, means going from C3 minus C to SL2C.
So did you get some period of the form in the SU2, which is three-dimensional sphere?
That's right. SL2C has a trick sphere, and the period of the synthetic form, or the Calabi-Yau form is an H bar.
Okay.
And so, this is we got to this before understanding all of this other stuff historically. So the first paper I wrote with Kevin on crystallography was about studying the D model on SL2C and comparing it with the gauge theory associated to C2.
So for those who know something about mirror symmetry, so you have a three-dimensional Calabi-Yau, which is a group SL2C.
Yes.
And you look for a B model, which for us, or for those, it should be some, I don't know, dB Koch on this Calabi-Yau.
Yes.
What's remarkable about it?
So we need to see, it's a non-compact Calabi-Yau, so we need to talk about boundary conditions. We need to decide what we do when we say dB Koch in SL2C. And establishing a good dictionary is fundamentally very important in holography. So with Kevin, we found some boundary conditions on SL2C, which allow you to develop the holographic dictionary. So that, and I don't think I would be able to go into detail for that.
Yeah, okay, just follow your plan. Yeah.
So just to say, it's not enough to say, oh, I do dB Koch in SL2C. It's really important to very carefully decide what happens at infinity. And you need some kind of a relative category to the boundary and think about the boundary the right way. So you can compactify SL2C, certainly, to get some normal cross divisor.
Well, it's something quadratic, yeah.
Yeah, that's right. It's a quadratic in CP4.
Yeah.
So when you say put the boundary conditions, does it mean like considering coherent shears with support on some compact thing or something of that sort, or is it something completely different?
So it's a bit funny. So the boundary, the divisor at infinity is essentially a product of two CP1s.
Yeah.
And the boundary conditions treat them treat them asymmetrically. So one CP1 is literally the CP1 where the original chiral gauge theory was living. And the other CP1 is auxiliary. Because it's related. Essentially, one of the CP1s comes from the C direction in C3 mod C. And the other one comes from the boundary of C2.
So you have what? Family of vertex algebras or what?
Yeah, so in principle, there is a way to extract a vertex algebra, a Poisson vertex algebra, by looking at polyvector fields on SL2C. But the details still confuse me.
Yeah. But you said that it's in your paper with Kevin, yeah?
Pieces of it. I still don't feel we had the complete story. So,
but still, even independently of your goals for people kind of interested in DB-Koch. It's some category which kind of should be understood looking at your choice of compactification. Okay, good. All right. Sure, go on.
So to talk about categories, it will be easier to modify the theory, and we'll get there in a moment. Okay, so now, as I said, this Poisson-Chiral algebra is complicated. I've been struggling with it a bit. Keiju has a paper about it. Keiju, sorry, has a paper about it where he does some interesting calculations. In the paper with Kevin, we sort of took a very small piece of this Poisson-Chiral algebra. There is a piece of the vertex algebra, which can be linearized safely. And it gives you sort of a global symmetry algebra, we call it. Sometimes it's called the wedge algebra. So it's the model of the vertex algebra which kill the vacuum both at 0 and at infinity. So they're sort of well defined on CP1. This is, and every operator contributes just a few modes, like the stress tensor contributes an SL2C. But it's still something which we could compute explicitly, and we matched it to polynomial vector fields in SL2C. So you could sort of see the geometry emerge from the vertex algebra calculations. To see more, we started adding D-branes. So there are two ways to modify the theory. One way is to add fundamental degrees of freedom. So we add two-dimensional degrees of freedom. They live on the whole complex plane, and they are transformed in a fundamental representation of the gauge group. So they're allowed to build mesons, which are operators in an extended vertex algebra. You can go to the same rigmarole. You get open-closed Poisson-Chiral algebra, which has both, lambda brackets between. There are sort of two lambda brackets: a closed lambda bracket and an open lambda bracket. Closed lambda bracket maps traces to traces. The open lambda bracket might map traces and mesons to mesons, or mesons and mesons to mesons. It's the analog of this sort of Q or Q closed and Q open that we have here. And you can build a open-closed 3D sigma model out of it. And you can compare it with the B model reduced on S3, where you now have both holomorphic Chern-Simons theory and BCOE theory. So concretely, the forms like zero comma bullet forms on C3 mod C give you the open modes. So again, there are some theorems in homological algebra I want to stress again, as before. Although there is a notion of quasi-isomorphism of classical 3D theory. And so here will be a conjecture that the classical 3D theory from BCOE theory is quasi-isomorphic to the classical BCOE theory from the traces. And there will be another similar statement for the open strings. I'm not going to describe in detail, but basically, you can just try to do the same things you did that I was discussing for the matrix model.
And when you write recover DB-Koch, recover from what?
So what I mean is that these kind of modifications give you space-filling D-branes in SL2C. So you see things like holomorphic functions on SL2C. In particular, you can start doing complexes of space-filling D-branes and build some piece of DB-Koch, presumably, while keeping track of what's happening holographically, meaning, everything you do must have a meaning in the quantum field theory. So I'm not sure you can get everything in DB-Koch. You get some pieces of DB-Koch which have a meaning in the holography.
But I'm confused. If you have polynomials, whatever, zero peak polynomials on SL2C, you just look for whatever dg modules which are projective over this part without the differential. It's something which it's a dg category which is quasi-isomorphic db-Koch.
Yes, absolutely. So that category you define geometrically. If you run through the isomorphisms I'm hinting about, this will become something in the quantum field theory. So it means you'll have added some modifications and perhaps some extra terms in the Lagrangians, in the differential, to do something. So you have established some dictionary between modifications of the great gauge theory and this category db-Koch.
Okay.
That's what I mean, recover it db-Koch. So recover it in the gauge theory to establish a good dictionary. There is another thing you can do, which is to do determinants. So these are things you do at one point on your complex plane to define an operator, a determinant of something. And again, you can study these operators. I studied them I started studying them in a paper with my student Kaja Budzik. We studied correlation functions on the complex projective plane of products of several determinants. We found these correlation functions had some kind of large n saddles. I will not explain the details, but at the time we matched them with holomorphic curves in SHUC. So these collections of determinants match D-branes, coherent sheaves supported in dimension 1 inside SHUC with certain shapes at infinity.
Oh, it's interesting. I tried to invite her, but she didn't respond. Probably. Modern girls, yeah.
A reminder.
Yeah, maybe for the next year. All right.
And so now you might complain that we're getting now the same type of coherent sheaves in two different ways, but that's okay. I mean, if you turn on them, you can turn on modifications everywhere, but then you can kill them almost everywhere, and you get modifications at points. So it's complete, it's consistent. But determinant, they're cute in their own way because they really give you a way to understand notions like large and saddle, which I completely overlooked in the discussion until now. But just to say, the same quantity might have multiple perturbative expansions, which correspond to different objects holographically.
So they are correspond to different critical points
of something, that's right, of an effective action.
Mm-hmm.
Okay, now as we just have 10 minutes left, I was thinking.
You have more. If you don't.
Well, I've been going a bit fast, perhaps. Perhaps we should ask. Are there more questions?
No. It's Chern-Simons. It's something which maybe mathematicians know about.
Yes.
So
that's right. I only have a few slides left, so questions are very welcome. Otherwise, I'll run out. So I want to study now UN Chern-Simons theory. Very, very well understood mathematically. There are several papers. There is a beautiful upcoming draft by Williams and others, which has just everything that you could possibly need to understand slides. Anyway, simple action and defines the topological field theory. So in particular, there is a E3 algebra, E3 factorization algebra in R3, defined over perturbation series in H bar. The E3 algebra is a bit boring because the single trace operators are just traces of A to the n. And
sorry, David, you see, since it's mathematics seminar after all, R3 is non-compact, and typically Chern-Simons. Well, you wrote BV, but you can write CS.
yes.
It's on the compact manifold, yeah. And here
it's your choice. It depends on what you do. If your objective is to define something local, like a factorization, an E3 factorization algebra,
it doesn't matter.
Then R3 is good.
Yeah. Okay.
Later on, I will work implicitly on R times a sphere to a bit more control it, spatial infinity. But anyway, it's a small detail. The E3 algebra itself is a bit boring, I was saying, because it only contains the traces of A to the 2n plus 1.
So I am confused because I see n and k. You see GLN, which probably means...
wait, I am still at the first line.
Okay.
The bulk period, the Chern-Simons theory by itself in flat space is boring. I think we can agree on this.
Yeah.
In principle, there is only 3 factorization algebra, but it's a very simple thing. I don't know if there are some interesting higher operations. I don't think so. Maybe there are. But anyway, I'm not gonna try to do something with it. Instead, I'm gonna modify the theory right away. So I'm gonna add some fundamental degrees of freedom that live on the line. Just a bunch of fermions, 1D fermions. So there is a kinetic term, which is a differential along the line, and then like coupling to the connection.
What is
K is the number of fermions.
All right.
So I have K fundamentals. I mean, there are K times N psis and N times K psi bars.
I'm trying to see how these products classically generate representation of GLK.
Well, I was
simply literally.
Yes.
Because, all right.
Yeah, that's right. In quantum mechanics, you do something like you have a psi, bar psi.
Multiplied.
Algebra.
Yeah.
Classically, there's a Clifford algebra.
Yeah.
And then the bilinear to the Clifford algebra, and the Clifford algebra generate UGLK.
Yeah. Okay.
And what I'm trying to say is that somehow, if you look at the classical factorization algebra on the lines, that's it. So this also looks pretty boring. But it's not completely boring, because as you turn on quantum mechanics, this UGLK gets deformed to UH bar GLK. Now, of course, you'll tell me this is not really a deformation. UH bar GLK is isomorphic as an algebra to UGLK. That's true. What I really mean with this statement is that to define the system, you really need to regularize it a little bit. You regularize it by separating the K lines in space. You keep them parallel to each other, but you separate them in space.
So then H bar appears when you interchange two lines, like as an R matrix or what?
If we were talking about UQGLN, that would be true. So UQGLN, you see in the coproduct. So these lines start their life as representations of UN, but they become representations of UQGLN if you keep into account their fusion.
Yes.
Here there is a related statement, but it's not stated quite in the same way, because we're not talking about UQGLN, we're talking about UQGLK. So what's going on is the following. You separate these lines, and then the bilinears become open Wilson lines, meaning that to contract a psi from one line with a psi bar to the other line, you need to parallel transport the connection from one point to the other. And if you open this paper, Quantum Skew Hole Duality by the Kanitzer and a bunch of other authors, they observed that these open Wilson lines satisfy the algebra of a quantum group, where the E's are sort of lines going one way and F's are all lines going the other way. And when you bring them across each other, when the endpoints touch, there are some scaling relations that reproduce the quantum group. So this is what I'm really meaning with UH bar GLK, that when you separate the lines, the algebra bilinears get deformed. And furthermore, if you reorganize the lines, you braid them around each other, you get the wild group of this quantum group.
Say it again.
So the quantum group, UH bar GLK as a wild group, which is the braid group. And
well, it's a little bit more than than braid group. It's called quantum while group. That's why I woke up, because I invented it long ago.
That was not a precise statement, but it's related to the braid group at least.
Yeah, it's related because it's related. But there are more relations than just braid group relations. Yeah, okay.
That's true.
And they appear as what in this picture?
So you literally braid the lines, and these rungs stretched between them get transformed in some way. When I braid two lines, the rung will get tangled, and then I can disentangle with the skein rule.
Oh, I see.
And the result
it's more interesting than I thought. I thought that you get something like R matrix, but this quantum while group, it's not related literally to the quantum. Okay, so it's interesting. Yeah. And you say that it's in this skew-Hooft duality of Kamnitzer.
Quantum skew-Hooft duality. That's right.
Yeah. Okay.
And to be precise, you get a quotient of UQGLK because you're acting on a specific collection of irreducible representations, which are the ones labeled by Young tableau of size says n, capital N. The length is capital N, and then there is some height, which is roughly the charge you put at infinity, the fermion number. So this quantum mechanical system has, the Hilbert space, which is this representation on which these rung operators act as the quantum group. Okay, so this is the quantum.
So on your graph, you have a GLK and a GL capital N, and on your picture you have a little small n. Is that the K?
No, the little small n is sort of a fermion number. I should have put a sum over n, and somehow it disappeared.
Also, that's the number of irreducible representations.
That's right. It was supposed to be sum over n.
So you mentioned about quantum duality.
From 0 to k. That's right. Mm-hmm. Yeah, that's right. Skew-Hooft duality tells you that the exterior algebra of CKN decomposes as a sum of representations.
Okay, I see. K actually in one direction that's corresponding to level K, right?
That's right. So there is a sum of representations of UN and representations of UK, which are with transposed representations.
Yeah, this is some sort of a level rank duality.
Yes, absolutely. So in order to project on things that are trivial, gauge invariant under UN, you want the height of T to be n, and then this becomes the length of T transpose.
Okay, yeah,
so
thank you.
Think about a representation with very large spin. And now when we do the Hooft expansion, we're going to send h bar to 0, but keep an h bar fixed. And this gives us an interesting classical limit of the quantum group. So now I tell you there's a phase space, which is the classical limit of the action of the quantum group on this representation. If you want a toy model of this, you can think about the action of SL2 on a sphere. When you quantize the sphere, you get irreducible representation of SL2, whose spin is roughly the radius of the sphere in units of h bar. That's a fuzzy sphere. So this is like a gigantic generalization of the fuzzy sphere Q-deformed.
So can you repeat it again? Because you see, and kind of when I was much younger, I also wrote some papers on odd dimensional quantum sphere, action of the quantum group on it, and the other stuff jointly with Waxman. And so how do you see it? So classical limit of this whatever quantum group which you realize in terms of this line, Wilson lines or whatever you call it.
Let me see. What is the classical representation theory statement, right? You take orbits of a group of
yeah, you can take some vector bundle on the coadjoint orbit. It depends on what
you do geometric quantization, right?
Yeah, you can do geometric quantization.
And then the result is something like a representation of n lambda.
Hold on. But when you say sphere, do you mean just SL2 or general GLK?
So if K was 2,
yes. So or whatever, then your orbit is two-dimensional sphere, yeah, and you realize okay.
There is an S2. It can be complexified to an AD singularity, to a square, to a complex symplectic manifold, if you really want. I mean, I definitely want, because I want a complex phase space typically.
Yes. Okay.
And then you quantize it, and you get a representation of UG, which is.
You see, the thing is that if you do it in this way, it's not really. Hold on.
I need a deformation of that because I need UQ. So I need to replace the sphere with something else.
It's not really a big deal because your orbit is a quotient of the algebra of functions by the ideal.
That's right.
Then your algebra of functions is, in fact, when you quantize it, it becomes UQ, SL2.
Yes. Absolutely.
And so then there is a corresponding ideal, probably given exactly by the same equation.
That's right. It's some orbit in the Poisson-Lie group.
Yes, I understand that story. Yeah, so it's indeed a sort of a Borel-Weil, realization. Okay, good.
Now, this phase space is a beautiful realization as a character variety. Actually, it has two realizations.
Again, which phase spaces?
This phase space whose quantization gives us this family of representations.
So, but classically, they are what? Total spaces of some line bundles on the orbits, or what?
Well, so you could definitely try to describe them as just an orbit of the Poisson-Lie group.
Just an orbit. Okay, good.
Yeah, that's fine.
Have no problem with that.
The Poisson-Lie group is a character variety.
Poisson-Lie group is not a character variety.
Yes, it's a character variety associated to a disk with two punctures, with Stokes phenomena.
No, but it's cluster variety. But it's cluster variety. It's not for SL2. Yeah, maybe, but for others.
No, for all, it's always a character variety.
No.
Yes.
Hold on.
I claim the G dual is a character variety. This character variety. I mean.
You mean okay? So you're not talking about dual to Lie algebra. You really look at the dual Poisson-Lie group.
Yeah, the one whose quantization is the quantum group. Absolutely.
The one quantization of algebra of functions on which is a quantum group.
Yes, that's right. Or G dual quantizes to the quantum group. So OQ G dual is UQ G.
Yeah, it's like product of two Borels with a common Cartan or something.
Absolutely, yes. It's a Stokes data of an irregular singularity.
Yes, so that's what you mean. Okay, good.
This is a GLK character variety. Now, there is this beautiful fact that that same character variety has a completely different description, essentially related by a Fourier-Mukai transform, which is a rank n character variety on the plane with a collection of regular singularities. These regular singularities are literally the positions of the original line defect. So this plane is just the physical plane where I put the line defects originally. Now there are classical monodromies.
Yeah, but what's the rank of the local system?
N.
N small, N capital, M
little n, small n, small n.
Small n, and again, sorry, the number of points is what? Small n?
K. No, K.
It's K. Okay. Yeah, so I'm confused. So, okay, there are K points, and there is a local system of rank n with now regular singularities, because you made the Fourier transform of this regular story.
And there are minimal regular singularities. So the monodromy is 1 plus a rank 1 matrix. And there is an overall constraint that the overall monodromy at infinity is the multiple of the identity e to the 2 pi I and h bar. So that's where n enters, just as the holonomy at infinity.
Okay.
So this is quite a pretty description. I like it because holonomy, diagonal holonomy multiple of 1 at infinity is the same as saying it's a twisted connection. So a rank n twisted connection, or a twisted D-module if you apply Riemann Hilbert. We don't really need to, but let's do it just for fun. It's a twisted D-module on CP1. But twisted D-modules on CP1 is how you describe certain A-branes. So if you take the A model on the deformed A1 singularity, and you ask me, what are the D-branes there? Well, the deformed A1 singularity is a twisted cotangent bundle, and so D-branes are a twisted D-module.
And so they're twisted by
an h bar.
By an h bar.
That's right.
Yeah.
So we got D-modules. We really got the categorical D-modules if you do deformation theory, just because if you take the direct sum of two connections, you look at the infinitesimal deformations, you get the morphisms. So by looking at these parallel lines in Chesamont's theory, we got the categorical D-modules. You can even add, yes?
Are you saying that this category of lines is, it's mathematical state equivalent to the category of D-modules with K regular singularities?
Yes.
Maybe twisted D-modules.
Twisted D-modules.
On CP1 with K regular singularities.
Yep.
And this is it.
Yeah.
Okay.
That's right. Now you can, add a bit of time evolution, slowly braid your lines, try to make knots, perhaps, or links. And, a bit at a time, you sort of the emergence of a three-dimensional story, in the sense that as you evolve time, time evolution sort of evolves your phase space, you get what look like, to me at least, like constructible sheaves of the modules. Like time, at each point in time, you get a D-module, but sometimes jump or evolve.
But what I'm confused, so you have this, they will be constructible sheaves on the line.
On the line, that's right.
On the line with values in the category of D-modules of certain sort.
Yes.
With regular. But if it's constructible, there should be singularities somewhere. And what are these singularities?
Right, because, suppose I'm trying to do a knot, right? I do something, I'm just, even the knot, right? If I cut it at some point in time, I'm going to see the module with two regular singularities. If I cut it in the future, there is going to be the module with no singularities. And so in between, something has jumped.
All right.
And it jumps with very specific rules.
And so what are the rules?
there are some explicit correspondences between these phase spaces.
Hold on. But these phase spaces are more or less as monodromy.
Yeah, there's spaces of the modules. So, so there are correspondences between spaces of the modules.
Yeah, but the modules on CP1 with a fixed number, it even doesn't matter, with some number of singularities, it is determined completely by the monodromy. Okay, you have an addition, this twisting, it's twisted, but let's forget about it. So it's determined by monodromies.
Yes.
And maybe if you allow singularities to collide, then maybe some irregular singularities will appear.
Well, you want the singularities to, so there are some specific rules that allow two singularities to meet and cancel. The rules are...
it's strange. What are these rules? Where they come from?
From an explicit calculation in the Chern-Simons theory.
All right. So it's not possible to see them in this naive story with constructible sheaves.
Yeah, I've been trying. I mean, you can I think it's reasonably sensible, but yeah, I would love to understand it better. So you get rules which are reasonable, but
okay. So then there are some rules on what's happening when the phase transition comes, when you kind of the topology of the intersection gets changed. And you say that it's a cancellation, it's not appearance of irregular D-modules, as one can imagine. But you see, let me ask you, if you have this, well, let's think D-modules is just bundles with connections. Let's just think in this. So then when your singularities of the connection regular, when they collide or whatever, there is the Schlesinger type of equations of isomodromy type. And you say that you have different type of constraints, which...
No, I mean, I think in terms of the Schlesinger equations, you say something like, okay, when the singularities come together, there will be some monodromy eigenvectors somehow. How do I say that? No, sorry.
Yes, something can happen. For example, you can require, I don't know, that just residues are opposite and then disappear. I mean,
right. So typically, either the L's or the L duals will align as they come together.
Yeah.
So that gives you a fusion into a new regular singularity.
Okay, let me ask you a different question. This is a picture on the Fourier dual, or if you like, Borel plane. If you do it in the original character variety, what's going on?
You can. I have not explored it very much because somehow this picture is more physical. These are literally the lines. But definitely finish the question. I would love to understand better.
Because it's just you have family of D modules, you can describe their kind of changes, whatever, in terms of D modules themselves, but can ask what's happening for their monodromy data, and so that's it's equivalent. It's what's going on with Riemann-Hilbert functor. Yeah,
absolutely. So I've not formalized this. It would be nice to do so. Ben and Mary have written a paper where they formalize part of our construction.
Who did?
Ben Webster, sorry, and another postdoc here, Mary. Sorry.
Let's see.
Mary, I forget the first name. Sorry.
Okay, let me see, because I typically look at what Webster is doing. Let's see. And Webster. Okay. There is something. Zaimi.
Yes, that's right.
Not contact homology as a planar limit of I recall that they mentioned that they tried to understand something which you did, but since I didn't understand what they did, so I forgot about that paper.
Sorry,
but it was the last slide, so then.
No, there was another slide. Sorry.
There was another. You didn't send it to me.
No, sorry, you're right. It's done. It's done. Yes.
It's constructible shifts of the modules. So it's very interesting stuff. All right. Well, thank you very much. And now time for questions for those who want to ask. Because so many things that, it's. And from what you said, except of your paper, which has the same title as your lectures here, is there anything published?
I'm trying to write some drafts on the matrix models. I have a paper on the chiral algebras, which is the language was still a little bit less developed, but with Kuyo and other students. And the Chern-Simons, I have the paper on Chern-Simons for the link invariants.
Because it's story, about constructible shifts of the modules. I told you that it resembles something which we did with Maxim. At least maybe, I'm not sure about D modules, maybe about QD modules, but it's not really, for you probably it's not very important because it's a very general story.
No, absolutely. So I was using the modules just because I don't know Fukaya. And so
but that's the point. Many people here would be pleased to. From the Riemann-Hilbert point of view, this dual story with character variety should be not character variety, it should be Fukaya, of course. And so then it's kind of very interesting things. All right, so last time to ask David a question during his very stimulating lecture. Well, if not, thank you very much, David.
Thank you.
It was really great. Thank you.
It was great for me to talk about it and write it.
And anytime. So I would be glad to continue to discuss.